Now having talked about t-test, the next one is what? Variances, 2 population variance. Okay. So now we are going to ask sigma 1 square equals to sigma 2 square or sigma 1 square not equals to sigma 2 square, right. This is like comparing 2 population variance. Okay. Later on you will see that this is the one of the most widely used distribution, F distribution. Okay. So suppose I take, when you try, when you actually try different things and see which one is effective, is there at least, so suppose I try 5 drugs, I would want to know at least is one drug is effective or not. What is the kind of question you want to answer statistically? At least one drug is effective or not. You try 5 drugs and you want to know at least one drug is effective. You understand my question? I am not even comparing 2, I am asking what? 5 drugs, which is common, not just 2 drugs. I say I have a spate of drugs, I want to know at least one of is at least one of them effective. How do I go about doing this? How do I go about doing this? If one, at least if one is effective, if I understand one is effective, I will find out which one later on. Okay, there are 2 steps. I am now asking a question, look, I have 5 or 6 drugs or n number of drugs, I want to know which one is effective for this particular situation. Then I will figure out if something is effective, then I will figure out which one is effective. How do I do this statistically? What kind of experiments will you conduct, and what is, what is the metric you will see, what is the test statistic you will look for? Should I look in mean or should I look in variance? First question. Why variance? Should I look in mean or should I look in variance? Somebody said variance. You understand my question, right? 5 drugs, the resulting outcomes. Will you test the hypothesis on mean or will you test the hypothesis on variance? See, when you do mean, right, so I may actually do the statistics in, what I call mean, okay, test in mean, but we will see that, I may find out there is a, so what I want is all the means same, statistically equal to 0 or not equal to 0, right. If all the means, if all of them are statistically 0, that is none of the drug is effective or not, at least one is non-zero, then I am happy. I am not even asking which is non-zero, is mu1 to mu n is equal to 0 or not equal to 0. That is the kind of question we are asking. If I want to put it statistically, which drug is effective, I am saying all the drug has no effect, that is my null hypothesis. So the mean of all the effects is equal to 0 or at least one is effective. So at least one is non-zero. Now you can test this in multiple ways, okay, you can compute each mean separately and do it, or you can test it by comparing their variances. Okay. Later on we will talk about what is called as ANOVA, analysis of variance, which is used to answer this kind of questions. Okay. So variance will itself become very important even when you want to test the means. Okay. We look at it, we will come back to it later. Okay. So right now this comparing variances therefore is important. You will see that later on this comparison of variances is applied to our problem like n drugs, at least one is effective or not. Okay. It becomes a very important part in what is called as ANOVA, and that is where this F distribution comes into picture. Okay. F distribution comes into picture. Okay. So we are comparing the 2 variances, and by using what? So remember variance, what did we do? What is chi-square distribution? What is chi-square? Sum of squared normal random variables is chi-square distribution. So sum of n independent squared normal random variables is chi-square distribution, and it is a ratio. Remember it is a ratio, and the ratio followed a chi-square, that is sample variance by population variance followed a, I mean sample variance followed a chi-square distribution. Here F distribution is nothing but a ratio of 2 chi-square distributions. F distribution is nothing but ratio of 2 chi-square, and chi-square itself is nothing, chi-square itself is nothing but what? It is a sum of squared normal random variables, that is your sample variance follows a chi-square distribution. Okay, your sample variance follows a chi-square distribution. Okay, so here you are talking about F distribution, which is a ratio of 2 chi-square distributions. Of course, you assume that they both are independent. Till now we have not talked about relationships at all, so keep in mind even this is also no relationship, independent chi-square random variables. Okay, so the numerator is u degrees of freedom, the denominator is v degrees of freedom. So F is, it is W by y follows F distribution with u comma v degrees of freedom. Now degrees of freedom becomes 2. Okay, earlier it was T distribution or chi-square, it was only 1 degrees, I mean 1 variable, now it is associated with 2 variables. So u comma v degrees of freedom, because it is a ratio of 2 chi-square distributions. So this is what we have. So if you look at only one, you will have S squared by sigma square follows a chi-square, F is nothing but S1 squared by sigma square divided by S2 squared by sigma 2 square. This follows a chi-square degrees of freedom with numerator is n1 minus 1 degrees, denominator is n2 minus 1 degrees. So this is F n1 minus 1 comma n2 minus 1 degrees of freedom. Okay, so this is a F distribution. So the first sample, the first variable has variance sigma 1 square, the second set of samples has a variance of sigma 2 square, mu 2, mu 1, and this is my sample variances. So F is S1 square by sigma 1 square by S2 square by sigma 2 square. Okay, keep in mind this F distribution will be the most widely used distribution when we are analyzing questions like whether at least one of the method is useful or not, one of the drug is effective for a particular disease or not, particular underlying disorder, whatever, right. So F distribution is very important. We will later on look at what is known as ANOVA, which is called as analysis of variance. Where you will use this idea. Okay, F distribution will be the test statistic. Which you know, because I am talking about no. Why will I know? So how would I give confidence interval? My F distribution is a ratio. Okay, and what is my confidence interval? What is my confidence interval? For chi-square, what is the confidence interval? Sigma squared is lies between less than or this thing. So you have sigma squared I forget, this is n1 minus, okay, let me pull up that slide. So sigma squared is what? Sigma squared lies between, you can always write n minus 1 s square. So sigma square bound is what? This is my limits. So sigma square lies between n minus 1 s square by gamma 1 minus alpha by 2, and the other one n minus 1 s square divided by gamma alpha by 2. There also mu is there, but mu you take it as the null hypothesis, same thing. Okay. So your test statistic is simply S1 square divided by S2 square. Okay, and this follows, and this the various hypotheses are not equals to, greater than, less than, and again this is a non-symmetric distribution. So you will have alpha by 2 comma 1 minus alpha by 2, it is not symmetric. Only T and Z distributions we have seen is symmetric, both chi square and gamma distribution is, I mean F distribution is non-symmetric. Okay. So to give you an idea example, in this case I had simply sigma 1 square not equals to sigma 2 square as the null hypothesis, alternate, alpha is 0.95, test static is here, I know S1 square from data, I know S2 square from data, okay, I computed them. So if the degrees of freedom both n1 and n2 are 20, okay, so you know 19 comma 19 is the numerator and denominator degrees of freedom, you look at the f value, if it is 2.53, so any value greater than or 2.53 you reject the null hypothesis, and any value less than 0.40 also you reject the null hypothesis. So you computed, it is 0.85, okay. So what do we have? We cannot reject the null hypothesis because it is the between the interval 0.4 to 2.53, this is my acceptance region. Okay. So if you look at, go back, how did we get this formula itself? You have sigma 2 squared, so this is nothing but F distribution, right. So S2 squared divided by sigma 2 squared equals to S1 squared by sigma 1 squared divided by F, okay. So if you rearrange you will get sigma 1 squared by sigma 2 squared, compute what it is, okay, and this will be equal, this will be with F degrees of freedom n1 comma n1 minus 1 n2 minus 1, that is how you get this form idea F test, okay. You are comparing a ratio, right. If they are equal, what will happen? If sigma 1 square equals to sigma 2 square, what will be the value of F? I mean it should be, the ratio should be equal to 1, we are checking whether the ratio is 1 or not. Instead of subtraction we are checking for ratio whether it is equal to 1 or not. In mean we subtracted and we said whether the subtracted value is equal to 0 or not. In this case we are taking a ratio. Since it is a square quantity, subtraction does not make sense, that is why you take a ratio, okay, because its units are different. So we take a ratio and then see whether it is 1 or not, clear. That is what sigma 1 square equals to sigma 2 square and the ratio mean. If it is not equals to 1, if it is not statistically equal to 1, then we say the null hypothesis is false, is not accepted, its null hypothesis is rejected, clear.
Since we have to compare two population over here, we are using F distribution.
Yes.
About 5 or the example that we gave.
Which one?
About 5 drugs.
Then you cannot use this, this is only for 2, for 5 you have to do a different hypothesis, but that will also be in terms of F distribution, that will also be in terms of F distribution, but you have to use a model. We will soon look at that problem, that is called ANOVA, analysis of variance, okay. So the idea is following, right. So now your output, if you collect samples, your output whatever drug you give or whatever level of experiment you give, your output will contain noise, agreed, due to measurements. Now suppose you give a particular drug, you get an output, okay, say let us say output with certain noise, so there is variability in the data, and you say I treated with another drug, then there is you get the data with certain variability, okay. Now if I say, if I analyze the variability and then say look, this variability due to drug 1 is purely due to noise, then what does it mean? That drug is not effective. So the variability in the data and the variability in the noise, if their ratio is 1, what does it mean? The variability is purely due to noise, drug has no effect. Now if I compare and say no, look, the variability in the drug output, the variability in the output is not purely due to noise, then what else it could be? it could be because of the treatment you have given, right. So I can say when I want to compare multiple things, so I can say in ANOVA, this is the idea, at least I will throw you the idea, the overall variability can be attributed to what? Treatment plus noise, okay. I am only talking about variability, I have removed the mean, okay, I am removed the mean. The overall variability in the data is due to what? Could be due to the variability due to treatment and plus noise. So now if I compare, take the ratio of the variances and then say look, ratio of noise over overall variability, if that is equal to 1, what does it mean? Treatment has no effect, that is all, that is the idea we will look at, okay. So we will, this variance analysis will tell me whether which drug is effective, which drug is not effective, etc. So we will talk about it, but the idea is very simple, you divide the overall variability into treatment variability and noise variability, etc. This we will learn better if you once learn what is known as linear regression, okay. That is where we will be heading to, we should start learning linear regression thoroughly, okay, with assumptions, so that we can talk about ANOVA, okay. So this is the confidence interval on ratio of variances, which is again straightforward, sigma 1 square by sigma 2 square is less than or equal to S1 square by S2 square, again 1 minus alpha by 2 alpha by 2, you have to keep that in mind, okay. Now variance is done, the last one left is proportions, okay. For 2 samples they are left with proportions. So proportions, again the question is P1 equals to P2 or P1 not equals to P2, right. So the proportions is simply like your mean, so the same idea, so P1 minus P1 hat minus P2 hat, this is nothing but my x1 bar minus x2 bar, okay, minus mu1 minus mu2, this is P1 minus P2 divided by their square root of individual variances, okay. Again what is, this is Z distribution, so there is no degrees of freedom if sample size is larger, if sample size is small only then we will have a problem. This is for sample size larger, so there is no question, it is a normal distribution, you do not need to worry about degrees of freedom, okay, for large samples, okay. But for small sample what do we have? What will happen to the small sample? T distribution, again then it will become question of 2 equal variances or 2 variances not equal, exactly like your mean, this problem will arise and then we have to sort it out, okay. And if it is T distribution, then you have to, underlying distribution should be normal, but can I assume underlying distribution to be normal for proportions? Can I assume underlying distribution to be normal when I test for proportion? Proportion means what? Success versus, it is like probability, right, success or 1 minus success. So the underlying distribution is always what distribution? Binomial. So you cannot do proportion small test at all, small sample, okay. So it is very easy in directly telling T, but first of all the 2 binomial parameters, when you are talking about proportions you only talk about binomial distribution, because it is a ratio, it is proportions, success versus failure, that comes out of what? Only out of a binomial distribution, success and failure NCX P per x Q per n minus x, right. So it is all success or failure, 2 outcomes cases, 2 binomial parameters. So the underlying population is actually binomial, so you cannot assume the underlying population to be normal because we know it is binomial. So this proportions, it is only valid for large sample, for a small sample you do not even do proportions, make sense, clear. In fact in the previous case also for one population also we would have only done for large population, we would have not done for small population. I do not know how many of you looked at it carefully, okay. I would not have given a t distribution for p proportions. The reason is I cannot assume the underlying population to be normal because I know it is already binomial, okay. So you only work with large samples, and large samples, this is the idea. So there is no degrees of freedom etc here, simple, okay, and you can give the confidence limits also. This is the confidence limits, and since it is symmetric, z alpha by 2, z alpha by 2. Any questions? So far so good. So we have completed what I call 2 sample comparisons.